much. Yeah, thank you for having me on this beautiful conference for a stand-in of Bernd Beschoten, who is regretting it a bit that he's not here himself, but I'm very happy to take over for him. The talk I will be giving today has the title Towards Ballistic Spin Transport and BILAYER graphene. At the bottom you see two schematics of typical spin transport devices, where you have a spin hosting material, here graphene, and four contacts, two to the left and two to the right. The inner two contacts are ferromagnetic and separated by an insulator from the hosting material. Now the goal I want to present here is to build such a device which shows ballistic spin transport and where we are able to turn on and off the spin manipulation by an external electric field. In 2017, Dimitri also suggested to use bilayer graphene instead of graphene. Why bilayer graphene? Intrinsically, it has a rather weak spin orbit coupling of about 60 to 70 microelectron volts and is a zero band gap semi-metal. It's not working. Yeah, no, it's working again. Perfect. Thank you. But if you apply in such a structure a perpendicular displacement field, you break the symmetry between the lower and the upper layer, and you can open up a band gap. The size of the band gap can be tuned up to a few hundred millielectron volts by the strength of the applied displacement field. Now, what's even more important here is that at small momentum around K and K prime, these bands live on different layers. Here in this configuration, the valence band in red is hosted by the A1 atomic orbitals of the lower layer, while the conduction band in blue is hosted by the B2 atomic orbitals of the upper layer. Now, why is it interesting that each of these bands live in a separate layer of the bilayer graphene? That is, if we bring bilayer graphene into close contact with a strong spin orbit coupling material, for example, tungsten disulfide, we will have a proximal and a remote layer. And only the proximal layer will experience hybridization. So we have one layer which has strong spin orbit coupling due to the proximity, and one layer without strong spin orbit coupling because it's just too far away for hybridization effects. Due to this hybridization, there will also be some internal dipole forming, and we have an internal electric field. So it's expected to see a gap even without applying any kind of external electric field. Now here's where this layer tuning from before plays its role. The conduction band in this configuration is entirely hosted by the proximal layer, so it shows strong spin orbit coupling. The conduction band is hosted by the remote layer, so it only shows the intrinsically weak spin orbit coupling. If we now start to apply an external electric field, we can either apply it in the same direction to the internal field or in opposite direction. Going in the same direction, we move here to the right. We just increase the band gap. However, if we turn the electric field around, going to the left, at some value where the external electric field becomes larger than the internal electric field, we start to flip around which band is hosted by which layer. Now here, the valence band is hosted by the remote layer. If you keep your Fermi level all the time fixed in the valence band, you can switch by the sign of the external electric field between strong spin orbit coupling and weak spin orbit coupling. This is why Dimitri et al. Suggested to use bilayer graphene here in these kind of devices instead of single layer graphene. The first evidence for this layer tuning has been reported on in 2019 by Island and al. They characterized bilayer graphene on monolayer tungsten diselenide encapsulated in HBN with graphitic bottom and top gate. They used not transport penetration but penetration field capacitance measurements to characterize this device. The bright yellow areas are an indication of the gap opening, the blue areas are inside of the bands. Now highlighted with these white arrows, you see this point symmetrical feature, which is associated with the Fermi level being pushed through both split bands. And you can see that this feature either shows up in the conduction or in the valence band, depending on the sign of the applied displacement field. So really proving this layer tunability. They also extracted spin orbit coupling strengths of 1.7 millielectron volt. Another paper from the same year by Wang et al. Found 2.2 millielectron volt. Both values agree reasonably well with each other, and they are orders of magnitude larger than the internal value of bilayer graphene. So we really have now an on and an off state for our spin orbit coupling. In order to build ballistic spin transport devices, there are other requirements which need to be fulfilled. The bilayer graphene needs to show high electromobility and long spin lifetimes. We need an SO material which allows us to keep the high mobility of the bilayer graphene. We need a gating technology which allows us to homogeneously tune the gap over the whole device. And we need, in the end, some spin injection and detection contacts which allow for ballistic spin injection here. During the course of this talk, I will address different materials here, showing that CVD-grown bilayer graphene is actually an ideal candidate for these kind of devices. I will show you that graphite gates are must-have for homogeneous bandgap tuning, and I will show that tungsten dicyanide is an ideal candidate for its own material. Let's start with the CVD-grown bilayer graphene. In 2017, Michael Schmitz from our group reported here on a device based on CVD-grown bilayer graphene from our group. We grow graphene on copper foil. It starts out as a single layer graphene, and in the middle then you will see bilayer graphene as well after some time. This bilayer graphene can be picked up from the copper foil using an HBN stamp after the foil has been left to oxidize. Then Michael encapsulated this in HBN, etched every single layer part away, and just kept this hall bar shaped bilayer graphene HBN heterostructure. He placed an additional HBN on top, so he also included a gold top gate here. Using this gold top gate and the silicon bottom gate, he then started to characterize his device. Here on the top left, you see a typical resistance measurement as a function of top and bottom gate voltage for low temperatures. And this diagonal feature is very typical for bilayer graphene. The white dashed line denotes the charge neutrality point. Going from here into the edges, the corners, we increase the displacement field. So the increasing width is actually already an indication that we start to increase the gap. Perpendicular to this white dashed line, we can tune the Fermi level by this effective gating potential Vg. He also measured the XY conductance as a function of bottom gate voltage for different magnetic fields. And saw this nice Landau-Fane emergence, while large filling factors consisting down to low magnetic field, showing the high quality of this device. In the next step, he measured the conductance as a function of charge carrier density for zero applied displacement field for different temperatures as well. And you see that we have this kind of plateau here, which we indicate to a shifting from diffusive to ballistic transport here. The important thing is that we are able to fit these traces to extract the mobility values. And you see that especially for electrons on the, you see quite high mobility values. At 2K, we get above 150,000 square centimeter per volt seconds. At room temperatures, we still have 40,000. So we are checking already a lot of the boxes on the requirements I had. We are having high electromobility, we have also ballistic transport, and we have a large electromean free path of above 2 micrometers. These measurements, however, also show that you really need low temperatures to really fully utilize the potential of bilayer graphene. How does spin transport in bilayer graphene look like? In 2014, Mark Drögeler from our group reported on experiments in this inverted spin valve structures using exfoliated bilayer graphene. Inverted means here he's picking up graphene, or bilayer graphene in this case, and placing this onto some predefined contacts. The HBN then protects the graphene and the contacts from any kind of liquid solvents, allowing for high quality devices. Mark found here values of 1 nanosecond spin lifetime. Other experimental literature are these spin drift using exfoliated bilayer graphene. They found 3 nanoseconds and 7.7 micrometer spin diffusion max. There are also experiments with spin manipulations. Here are the spin interconnects in CVD-grown bilayer graphene. They found 2 micrometers and 250 picoseconds. There are many more publications on spin transport in bilayer graphene. I want to focus now on a recent work from our own group, where we are using these inverted spin valve structures with CVD-grown bilayer graphene. Here, Timo Biswanger from our group designed a new fabrication method. Starting out similar to Michael Schmitz with CVD-grown bilayer graphene on copper foil, he was able to pick it up with his HBN stamp, transferred it into silicon oxide, and etched this into a hall bar. And now comes this new step he introduced. He designed this PDMS droplet with PC foil on top. The PC foil has a high adhesion, so he was able to pick up this pre-etched structure and now place it also on some predefined contacts, and afterwards fuse the PC foil down to the silicon oxide. This method has several advantages. For one, it is fully dry. Again, the bilayer graphene never sees any kind of liquid solvents. Then he was able to really reliably pick up these pre-etched structures. The most important advantage is that due to the dome shape of this droplet, he's able to locally press down the CVD-grown bilayer graphene onto the contacts, enabling good contact between the bilayer graphene and the cobalt aluminum oxide. Let's take a look at some measurements. Timo measured at room temperatures in a diffusive transport regime, and as he had only one gap, he was not gate, he was not able to open up a gap. Here on the left side, you see again resistance measurement is a function of gate voltage, and you see this typical Dirac peak. The charge neutrality point of this peak is very close to zero applied gating voltage, so we really have small residual doping, meaning the HBN really protected our bilayer graphene. Here in the middle, you see these Handler curve measurements for parallel and anti-parallel spin contact configuration. Let me explain to you how these kind of measurements are done. Here again a schematic of the spin transport device. We have the two left contacts where we apply current, the two right where we measure non-local voltage. For zero applied out-of-plane magnetic field and both injection and detection contacts being magnetized in the same direction, we get here a peak. If we start to flip around the detection contact, we of course get here a minimum. Now if we apply an out-of-plane magnetic field, the spin starts to precess and we break away from this minimum and maximum, and we get essentially this curve here I'm showing in the middle. The width of this peak does depend on the inverse of the spin lifetime, meaning the sharper the peak, the higher the spin lifetime. Timo found values of 5 nanoseconds and 25 micrometers, which is of about 24,000 square centimeters per volt seconds. In the next step, he took a look at how he can tune the spin diffusion lengths and spin light, which will drop. If you start to increase the source drain voltage until a point C, where the energy difference between source and drain becomes equal to the band gap we introduced with the displacement field, then current can start flowing again beyond this point C. This also means that we can directly extract the gap value from the difference of point A to point C on the y-axis. Now for graphite-gated bilayer graphene, we find this nice singular diamond shape here, showing great tuning of the Fermi level, and as the area inside of this diamond is very homogeneous, it also shows that the gap is very clean. How does it look like for gold-gated bilayer graphene? We clearly do not have this singular diamond anymore. Instead, we have a lot of smaller diamonds slightly shifted against each other. The gap value we can extract here, black dashed line, is much smaller than what you would expect, white dashed line. What's even more of a problem for our spin transport devices now is this small shift of the diamonds relative to each other. This means we have a variation in doping and tuning across our whole device, making gold not sufficient for a homogeneous tuning of the band gap across the complete device. So we really need graphite gates here. Okay, I've addressed the spin hosting material, I've addressed the gate material, now let's address the SO material. Here we find that measurement of the 2D line widths of the graphene placed on different substrates. We are interested now in a substrate with strong spin-orbit coupling, so we have the band gap. I only need to address now if we have spin-orbit coupling. In charge transfer experiments, this is usually done by taking a look how weak localization is converted into weak antilocalization. Both are interference effects due to a path forming a closed loop and its time reversed. They emerge if you apply a magnetic field, which adds a phase and breaks your interference effects. Then weak localization starts to show as a dip in the correction to your conductivity at zero magnetic field, and weak antilocalization as a peak. These kind of measurements have been done a lot for graphene and tungsten diselenate. Here, for example, Wang et al. In 2015 measured the change in conductance as a function of applied out-of-plane magnetic field for different gate voltages. And you see the peak here in the middle is very narrow, so it's easy. Let's take a look at our measurement. Here we measured the change in conductance with applied out-of-plane magnetic field for different gate voltages, and we made sure to check both sides of the band gap. Now you might start to wonder, why do we expect to see some kind of these weak localization effects even though the mobility is so high? The answer is we use the trick in our device. The bottom gate is much broader than our top gate, so it tunes our leads. As for negative displacement field, the bottom gate being also negative, our leads are p-doped. With the top gate, we can truly choose how our doping is. For negative values, we are also p-doped underneath the top gate. For positive values, we are n-doped. In this case, we get p-n junctions at the edges of our top gate, forming a cavity, and thus are able to observe weak antilocalization. This part here is a zoom in here, and you start to see now clearly the peak, and if I average over all these traces, I get this nice weak antilocalization peak here in blue. Now, slowly shifting the displacement field to positive values, I destroy this weak antilocalization effect simply by destroying the cavity. Okay, we have high mobility, we have a large mean free path, we have a great tuning of the band gap, and I have shown you clear evidence of spin-orbit coupling. The next step we are currently still working on is to build such a heterostructure for spin transport devices, but this is not something I can show you yet. Let me conclude my talk. I've shown you that CVD ground bilayer graphene shows high electromobility and long spin lifetimes, being an ideal candidate for this tunable spin hosting material. Also, tungsten dichalcogenide is an ideal candidate for SO materials, and hopefully I've shown you that graphite gates are a must-have for homogeneous bandgap tuning. The only thing I was not able to address are the spin injection detection contacts. Here we are currently working on an approach where we want to incorporate into our heterostructure ferromagnetic 2D materials. This is also something we are still working on. With this, I'm at the end of my talk. I would like to acknowledge and thank all these people, either by working together on the measurements and providing data, or by material, or also by very fruitful theory discussions. And I would like to thank you for your attention.
Thank you so much. Do you have any questions?
Thanks for a very interesting talk, and I have two questions.
So the first thing is, like, as we know, like TMD, WF2, there's a lot of defects. It doesn't matter that how you grow, but it still has a defect. The question would be that what's the effect of the defects on, like gap formation and spin transport?
Okay.
And second question is because recently
with the chrome germanium telluride, I think we haven't tested anything else. It's very much at the beginning. We recently got also a glove box to start to test out material not stable in air. And we have no feeling yet which material is ideal. So I guess we will test these as well over time. But these ferromagnetic contacts are still very much at the start. Just recently we have students started to work on this. So the other question was the defects in tungsten dichalcogenide, right? At the moment we are still using exfoliated tungsten dichalcogenide as a material, which